Hello, happy week 26. Today we're going to debrief the double slit investigation from asynchronous class and come up with a relationship that governs wavelength, slit separation, and distance to the screen with slit separation for a double slit diffraction grating. And then we'll derive an equation for double slit and multiple slit interference patterns. And then finally, I'll ask you to do a little practice using these relationships for the diffraction and interference of light. Okay, so let's first take a look at the patterns from our activity during asynchronous class. All right, so I asked you to do kind of a qualitative observation on the first part of the experiment, and then I asked you to actually take data and confirm your observations with a graph. Okay, this will help us in the derivation of our quantitative relationship. So let's look qualitatively. So we should have seen the relationship between wavelength and fringe separation to be proportional. Oops. My daughter was playing with my screen the other day. Okay. The relationship between slit separation and fringe separation, that was inverse, right? As the slit separation got further apart, the fringe separation got closer together. And then finally, the distance to the screen versus fringe separation. So how far away the actual slits were from the screen that we were observing the interference pattern on. And that was proportional. Okay, so let us name some abbreviations again. So remember, wavelength is lambda, slit separation is lowercase d, distance to the screen. In the activity, it used L, capital L. Sometimes in some resources, capital D is used. Okay, and then fringe separation. Sometimes we've been using lowercase y. In other resources, they use a S for distance, I guess. Right? Remember in the IB data booklet, they use S for distance. Sorry, I'm so yawny. I haven't had enough coffee this morning. All right. So proportional, inverse, and proportional. So we could almost build an equation, like a first guess at an equation here. Fringe separation is proportional to wavelength, inversely proportional to slit separation, and directly proportional to fringe separation. That's a good first guess, huh? Now you could pick one of your graphs. If you ended up making any of the graphs and coming up with a line of best fit, you could actually, like, maybe if you picked this relationship, distance to the screen versus fringe separation, if you've got your graph and your line of best fit, if you know the value of the slit separation and the wavelength, take the wavelength and divide it by the slit separation and see if you get that as the constant. Okay, spoiler alert, you should. This is the actual equation. All right, so This is the actual equation relating fringe separation, wavelength, distance to the screen, and slit separation for double slit interference. Okay, so let's write this again. For double slit interference, fringe separation equals wavelength times distance to the screen over slit separation. Boom. Okay, and this is in your data booklet under topic 4.4. Okay. So let's actually, that was a pretty decent derivation. I mean, doing that experimentally. We could do this derivation using some trig here if we wanted to. So we could even do a similar derivation for a multiple slit interference pattern. Okay, so this is a double slit interference pattern. So what if, so all of these have similar angles. What if we follow a ray from right here, right where this distance is d, and this is our angle, and actually let's do this actually from the center, following a ray from the center like I was going to do before. Okay, angle D, this is S, right? And so we could say, first off, theta equals opposite over adjacent S over D. Again, using the small angle approximation, we completely ignore tangent, where theta is in radians. Do you remember that from last class? Where we can say tan theta equals sine theta equals theta in radians. And so this comes from a tangent function, opposite over adjacent. Okay. We can also say, right, if this is a point of constructive interference, actually the first point of constructive interference, we can say, right, d sine theta equals n lambda. Right, so that's the condition for constructive interference. And we got this d sine theta last class. We did that derivation last class. Okay, d sine theta equals n lambda, where that d sine theta is that path length difference. Path length difference equals d sine theta over n lambda. And then again, using the small angle approximation, d theta equals n lambda, where n is a whole integer number of wavelengths. Okay, so the central maximum right here, there is no difference in path length. So the central maximum is considered n equals 0. The first order maximum, the first bright spot on either side of that central maximum, is considered n equals 1, right? There's a 1 wavelength difference in the path length between the two waves that are converging there, all right? And so we could solve this for theta. Theta equals n lambda over d. Right? And plug this in over here. And we get theta equals, oops. If we set the thetas equal to each other, s over d equals n lambda over d. And then if we solve for s, okay. So here's another equation. This is not exactly the same as the one that we came up with on the previous slide. We've got an extra n here. Okay, so this is not for slit separation. This equation is for distance from, I'm going to write this in a place where there's more space here. This equation is distance from central maximum to nth maximum. What does that mean? Well, with this, you can use this equation to not just find the slit separation, but you can use that to find the distance from the central maximum up to the first next maximum, or the second maximum after the central, or the third, right? So this is the first maximum is n equals 1. This would be n equals 3, right? So the only difference between this equation and the previous one is this is distance to any of the maxima, where n, right here, tells you which maximum. Okay, and so this s is typically, in this equation, this s is typically capitalized, and you use as a subscript the maximum that you're calculating to. This isn't in your data booklet, so you've got two options for equations. The first one that's in your data booklet up here, right, gives you an equation for, this is fringe separation. Okay, the distance between any two fringes. And this equation down here gives you the distance from the central maximum out to any other maximum. Okay, so let's do just a small qualitative dive here with a few diagrams that you've seen in your textbook. Okay, so I'm going to actually pause here and I'll discuss these couple of diagrams in the second video.